Hi everyone, my name is Valerie and I'm an ECE student from Wayne State University. I'm going to be showing you a sample problem from ECE 2610 Digital Logic Design. This is from the Combinational Circuits section of the course, and in this video we're going to use multiplexers to synthesize this truth table into a few different logical networks and compare their strengths and weaknesses. So first let's review how multiplexers work. Multiplexers have 2 to the n inputs. They have n select lines and 1 output. So let's look at our most basic multiplexer. This guy is a 2-1 mux. So we're always going to have one output F, and since this guy is our smallest multiplexer, we'll only have one select line, which we'll call S. So we have one select line, meaning n equals 1, so we're going to have 2 to the 1 inputs, which is 2. So we'll call our inputs x0 and x1. So we can think of this kind of like a switch. Our S is our select line, and that's going to tell us which of these inputs we want to send to the output. So if S equals 0, we're going to send this guy, and F is going to be equal to x0. If S is equal to 1, we're going to send this guy, and F is going to be equal to x1. Now we can scale this up to a 4-1 mux. Again, we're going to have one output of F, but this time we'll have 2 select lines. We'll call them S0 and S1. And that's going to give us 2 to the 2 inputs. So we'll put 4 inputs right here, x0, x1, x2, and x3. So now we have 2 select lines, so that means we're using 2 bits to select which input we're going to send to the output. So if these guys are equal to 0, 0, we're going to send that initial option of 0, and F is going to be equal to x0. If we want to say that S0 and S1 are equal to 0 and 1 respectively, then we'll pick our 0, 1 option, which is that second one right there. And then similarly, we can get x2 with 1 and 0, or x3 with 1 and 1. So in the same way, we could scale this up even bigger to an 8-1 multiplexer, which is going to have 3 select lines and 8 inputs. And then we'd have all the same inputs, and we'd use 3 bits to select which one we want to send to F. So now let's try to approach this problem. So let's say that we are a group of chip designers, and our team needs to make a design of this truth table to send to our customer so that they can give us back some money. We'll see that we have 3 inputs here, so our first instinct might to be say, well, 3 inputs means 3 select lines, so let's use an 8-1 multiplexer. So we always have a single output of F, and let's use 3 inputs or select lines, A, B, and C. This will give us 8 possible inputs. 8. All right, so now we need something for these to select. This first line at the top will be selected when A, B, and C are equal to 0. So when A, B, and C are all equal to 0, that will give us an output of F equals 0. So let's put that right there. So when A, B, and C are 0, we select this guy, and we're going to see an output of 0 to F. Our next line will be selected when A equals 0, B equals 0, and C equals 1, which aligns with this line of our truth table. That's going to give us an output of F equals 0 again. Our next line will be selected when A equals 0, B equals 1, and C equals 0, which is this line in our truth table again giving us 0. And then our next one will be selected at 0, 1, 1, which is right here on the truth table, and that's going to give us 1 to send to F. Now, you've probably noticed that we've aligned this so that we can just follow our truth table all the way down. So for 1, 0, 0, we'll get an output of 0, and for the rest of these, we'll have an output of 1. So now let's evaluate this design. It certainly does the job, but I have a feeling that our customer isn't going to like it very much. This design is not very efficient, making it more expensive. We're only using constants as inputs, which means that we're not taking advantage of the relationship between our variables. So let's see if we can use a 4-1 multiplexer to draw an equivalent network that is more efficient. So the first thing we'll notice about our 4-1 multiplexer is that this time we only have 2 select lines. So let's use A and B, and we'll have to find some other way to incorporate C into this network. And 2 to the 2 is going to give us 4 inputs on our multiplexer. This first line will be selected when A equals 0 and B equals 0, which happens twice on our truth table. So we'll need to use that first line to represent both of these cases. Lucky for us, this is pretty simple because in both cases, F is equal to 0. So we can just use a constant to represent that portion. Our next line right here will be selected when A is equal to 0 and B is equal to 1. Again, this occurs twice on our truth table. A equals 0, B equals 1, A equals 0, B equals 1. So we'll use that to represent both cases right here. This time, however, F is equal to both 0 and 1, so we can't use a constant to represent the output. Let's see if we can find a relationship between the input and output to represent this. We can notice that when C equals 0, F equals 0, and when C equals 1, F equals 1, which means that we can use C to represent this case on the truth table. Even though C isn't always equal to F, it is when this line is selected, which is why we can put it right there. So next up is A equals 1 and B equals 0. Again, 2 cases, and we have outputs of 0 and 1 for F, so we can't use a constant. We'll do the same thing here. We have 0 and 1 at the same time that C is 0 and 1, so we can again use C as our input right here. And then for our very last case right here, A equals 1 and B equals 1. Last section of the truth table, both of these give an output of 1, so we can just use a constant to represent this. So now let's evaluate this design. It is certainly more efficient than our 8-1 multiplexer because we have less inputs and we're using our variables to our advantage. So let's say we send our design off to the customer and they like it. But then the financial team comes in and says that it would be cheaper to use 2-1 multiplexers because the parts are cheaper. So let's see if we can make an equivalent network with just a 2-1 multiplexer. So this time we're only going to have one select line because this is our smallest multiplexer. Let's say we'll use A to represent this, and then we'll have to use B and C somewhere else in the network. Again, 2 to the 1 is going to give us 2 possible inputs. So when A equals 0, we'll select this line, and when A equals 1, we'll select this line. This means that we'll need to use this line to represent this whole portion of the truth table, and this line to represent this whole portion. So let's start with A equals 0. So in all of these cases, A is equal to 0, and we need to use that to create an output of F. We can't use a constant because F is not consistently 0 or 1. We also cannot use just a single variable like our previous example because our values are not consistent. There's no case where F is always equal to A, B, or C. So let's see what we can do. A is always 0, so that's going to be redundant information. Let's see what we can find with just B and C to relate to F. we'll notice that the only time f is equal to 1 is when both b and c are equal to 1. That looks like an AND gate, so why don't we add that to our truth table with inputs b and c? So when a equals 0, we'll select this line, and then when b and c are both 0, we're going to send an output of 0 all the way to f. That's going to be the same for this second case and the third case, and then for this fourth case, when a equals 0, b equals 1, and c equals 1, we'll send an output of 1 to f. So now we've used just this line of the multiplexer to represent this whole portion of the truth table. So now let's see what we can do when a equals 1. So this time a is equal to 1, so we're going to use that to represent this whole portion of the truth table with just this line. Again, a is redundant, and we're going to use b and c to find a relationship with f. This time we'll notice that anytime b or c is equal to 1, we're going to get an output of 1, and when they're both 0, we get an output of 0. That is an OR gate, so how about we put one of these right here with inputs b and c. So if a equals 1, we'll select this line, and then when b and c are 0, we'll get an output of 0. Or if either b or c is equal to 1, we'll get an output of 1. So now let's evaluate the design. This time, we've eliminated all of our constants from the input, which means we're taking full advantage of our variables and their relationship to the output to give us this truth table. This means that we're making our design more efficient, and we're using our customer's request to use a 2-1 multiplexer. So we'll send it to the customer, and everyone's happy, including the financial team. I hope this helps with your digital logic class. Good luck on your homework and exams.